Leo's Tech Talk. Video 14. Wi-Fi's first leap into 5 GHz. In our previous video, we explored 802.11b, also known as Wi-Fi 1, the standard that helped bring Wi-Fi into homes, offices, and public spaces around the world. But in the very same year, another Wi-Fi standard was introduced, one that took a completely different approach. This standard was IEEE 802.11a, commonly known as Wi-Fi 2. 802.11a was the first Wi-Fi standard to combine the 5 GHz frequency band with orthogonal frequency division multiplexing, OFDM. These two innovations laid the foundation for the speed, stability and efficiency of modern Wi-Fi networks. So, what made 802.11a so important? Let's find out. Key characteristics of 802.11a. Frequency band. The first major difference was its operating frequency. Unlike 802.11b, which operated in the 2.4 GHz ISM band, 802.11a operated exclusively in the 5 GHz band. This offered several important advantages. The 5 GHz band provides significantly more non-overlapping channels, allowing many wireless networks to operate simultaneously with much less interference. It also avoids most of the interference generated by common household devices such as microwave ovens, cordless phones, and Bluetooth devices, all of which typically operate in the 2.4 GHz band. This resulted in a cleaner and more reliable wireless environment. Channel bandwidth. Another major improvement was the channel structure. Unlike 802.11b, which used 22 MHz overlapping channels, 802.11a introduced true 20 MHz non-overlapping channels. This made wireless channel planning much simpler and allowed multiple nearby access points to operate without interfering with each other. As wireless deployments grew larger, this became a significant advantage. Modulation technique. One of the most revolutionary features of 802.11a was the introduction of OFDM. OFDM stands for orthogonal frequency division multiplexing. Instead of transmitting data over a single carrier, OFDM divides the wireless channel into multiple, smaller subcarriers that transmit data simultaneously. This makes wireless communication much more efficient and highly resistant to reflections and multipath interference. Thanks to OFDM, 802.11a supported a theoretical maximum data rate of 54 megabits per second, nearly 5 times faster than the maximum speed offered by 802.11b. Real-world throughput. But just like every Wi-Fi standard, theoretical speed is different from real-world performance. Protocol overhead, acknowledgements, retransmissions, and shared medium access all reduce the actual throughput. In practice, TCP throughput typically ranged between 20 and 25 megabits per second, while UDP throughput could reach approximately 30 megabits per second under ideal conditions. So remember, the advertised data rate is always higher than the actual throughput experienced by users. Range. Operating at a higher frequency also introduced one important trade-off. Signals at 5 GHz experience greater free space path loss and penetrate walls less effectively than signals at 2.4 GHz. As a result, the typical indoor range of 802.11a was around 25 to 30 meters, while outdoor line-of-sight communication could reach approximately 75 to 100 meters, depending on the environment and antenna configuration. Although the coverage area was smaller, the cleaner spectrum often resulted in more consistent performance. Media access control. While the physical layer changed dramatically, the media access control remained largely the same. 802.11a continued using the distributed coordination function, or DCF, based on carrier sense multiple access with collision avoidance, commonly known as CSMACA. Before transmitting, a wireless device first listens to determine whether the channel is already in use. If another device is transmitting, it waits. Each successful transmission is confirmed using an acknowledgement frame, and lost frames are automatically retransmitted. These mechanisms help ensure reliable communication across the wireless medium. Adaptive rate selection, ARS. Another important feature of 802.11a was adaptive rate selection, or ARS. Rather than always transmitting at the highest speed, the device automatically adjusts its data rate according to signal quality and interference. 802.11a supports 8 different data rates: 6, 9, 12, 18, 24, 36, 48, and 54 megabits per second. If the signal becomes weaker, the device gradually shifts to a lower data rate. As the signal improves, it automatically increases the speed again. This allows Wi-Fi to balance performance and reliability, while maintaining the connection. Interference susceptibility. One of the biggest advantages of operating in the 5 GHz band is reduced interference. Unlike the crowded 2.4 GHz spectrum, the 5 GHz band is largely free, from interference caused by everyday household devices. However, certain portions of the 5 GHz spectrum are shared with weather radar and other licensed systems. To prevent interference with these systems, later Wi-Fi standards introduced dynamic frequency selection or DFS. DFS enables an access point to detect radar signals and automatically switch to another channel whenever necessary. Impact and legacy. Although 802.11a was not as commercially successful as 802.11b, its technological contributions were enormous. It introduced 5 GHz operation, also introduced OFDM modulation. These two innovations became the foundation of every high-performance Wi-Fi standard that followed, including 802.11g, 802.11n, 802.11ac, 802.11ax, and today's Wi-Fi 7, based on 802.11a. In many ways, 802.11a shaped the future of modern wireless networking. Security. Like the original IEEE 802.11 standard, 802.11a initially relied on WEP, or wired equivalent privacy, for wireless security. It did not introduce any new encryption mechanism of its own, instead inheriting the same security architecture from the original 802.11 MAC layer. However, security researchers soon discovered several weaknesses in WEP. These vulnerabilities eventually led to the development of much stronger wireless security technologies, such as WPA and later WPA2, which significantly improved the protection of Wi-Fi networks. Recap. Although 802.11b made Wi-Fi popular, 802.11a introduced many of the technologies that power modern wireless networks today. Its move to the 5 GHz band, adoption of OFDM, and support for much higher data rates laid the groundwork for every high-performance Wi-Fi standard that followed. How many of you still use 802.11a, and which channel? Let me know this in comments. In our next video, we'll explore 802.11g, the standard that combined the long range of 802.11b with the high-speed OFDM technology introduced by 802.11a.